A very good evening to everyone. I hope all of you are doing good. I'm Anirudh, a BSc second year student at Chennai Mathematical Institute. A huge thanks to all of you for attending the penultimate lecture of the 2021 edition of the STEMS lecture series. Today, we're honored to have Professor Suvrat Raju of the International Center for Theoretical Sciences, or ICTS in short, Bangalore. His research interests are in string theory, quantum gravity, and quantum field theory. Professor Raju obtained his PhD from the prestigious Harvard University in 2008. He has many accolades in his name and has authored or co-authored dozens of papers. And he is very well known for his excellent oratory skills and his ability to convey things in a very simple fashion. So today, Professor Raju will take us through the exciting and seemingly ever mysterious journey through black holes and the reversibility of time. So just a quick instruction, please use the chat box for your questions as always, and we'll get them answered. So without further ado, over to you, Professor Raju. I hope all of you enjoy.
So thank you very much, all of you who've joined. And thank you very much for the organizers for asking me to give this lecture. I just thought I'll tell you about some I was instructed to keep this lecture at an elementary level, but I thought I would try and do as best as I can in keeping things at an elementary level and also trying to expose some of you to some of the ideas that people have been talking about in theoretical issues about black holes. I thought I'd start with something very basic, since this is, which is something which all of us know and where we could start with. The issue of black holes and reversibility of time that I'm going to talk about is eventually a question about quantum gravity. So before we start talking about quantum gravity, it's useful to remember how we reached this theory of gravity and what was the perspectives and the history of that story. And the story of gravity, the modern story of gravity, in a sense, starts with something that we all know and learn very early on in school. And that is just the Newton's law. The Newton's law was discovered by looking at trying to study, the motion of planets, like the planet Earth around the sun. And it's a very simple and elegant law. And it tells us that, if you have two such astrophysical objects like the sun and the Earth, then there is some rule for the force, the gravitational force between them. And the rule for the gravitational force is pretty simple. It says that the force is proportional to the product of the masses divided by the square of the distance between the objects. And so, if the objects double in distance, then the force goes down by a factor of 4. If you increase the mass of one object by a factor of 2, the force goes up by a factor of 2. And there's some constant of proportionality that's called the Newton's constant that appears there. Now, this rule was initially developed to study planetary orbits, but something that's relevant and important for us to realize is that, in fact, this rule is a very successful rule. We've understood Newtonian gravity now for maybe more than 300 years, and it's, in fact, a remarkably successful physical theory. And that's because even though we developed this theory by studying the motion of planets, it in fact happens to apply at a completely different set of scales as well. For instance, if you wanted to ask about the motion of the moon around the Earth, there's no reason a priori that motion had to be given by the same law or had to be governed by the same law, but it turns out to be governed by the same law. And so the simple rule of the gravitational force between the Earth and the sun applies also to the Earth and the moon. In fact, the same rule also applies to the Earth and to objects like rockets. So if you wanted to compute the trajectory of a rocket to leading order, the trajectory of a rocket would also be very well computed by using this force for the gravitational attraction, the same rule for the gravitational attraction between the Earth and the rocket. And the same holds true, if you want to fire cannonballs, so if you want to throw a ball up and observe how fast it comes down. So the same rule, the same simple rule of applying the product of the masses and dividing by the square of the distance happens to apply for a very remarkable variety of scales. And so in this sense, Newtonian gravity was a very successful theory, and it's, a quintessential physical theory which happens to apply to a remarkable variety of scales, is simple and is very accurate in its quantitative predictions. But about, maybe 120 years ago, people realized that there was something slightly unusual about the Newtonian theory. And the thing that was slightly unusual was as follows. if you remember the way we formulated the rule of the force between the sun and the earth, we formulated the rule by saying that the force is basically the product of the masses divided by the square of the distance. But now we can do a thought experiment. Okay, so what if some giant or some huge extraterrestrial civilization came and it displaced the sun from where the sun was currently? So the question one could ask is, when does the Earth get to know that the sun is not where it was, but that the sun has moved? So here's my friendly giant, and the friendly giant is pushing the sun from where it is. And the question is, when do poor a little us who are living on this Earth here, when do we know that the sun has moved? So of course we know that the light that's coming from the sun has taken about 8 minutes to reach us, and so we know that the light that's coming right now, I can see the sun out of my window. The light that is coming, if even if the sun is moved, will not actually change for about 8 minutes. But if you look at the Newtonian force law for gravity, it suggests that the force is proportional to the inverse square of the distance, and this would suggest that the moment somebody moved the sun, the force between the Earth and the sun would change, and we would feel that because the orbit of the Earth around the sun depends on this force, and if the force were to change, then the orbit would change. So if you were to take Newtonian gravity very seriously and you were to believe in it exactly, then this would suggest that the Earth would know immediately that the sun has moved. But in fact, we realized about around the same time, 100 years ago or 115 years ago now, that this is not quite correct. And by thinking about many other physical phenomena, people came to the realization, some of the people who were involved in this were Lorentz and Poincaré and Einstein. People came to the realization that information shouldn't travel faster than the speed of light. And there was a theory which was formulated around these ideas and around the issue of understanding what is the notion of simultaneity in time, and how things lengths might change if observers are moving with speeds relative to each other. And that theory is called the theory of special relativity. But what's important for us is that the theory of special relativity does tell us that there is a limit to how fast we can transmit information, and we shouldn't be able to transmit information faster than the speed of light. And of course, if this is correct, then this idea that we get from Newtonian gravity, which is that if a giant were to go and were to move the sun, the Earth would know about it immediately, is clearly in contradiction with this principle of special relativity that we learn from other physical phenomena and have also checked to great accuracy in many different settings. And therefore, the Newtonian theory, which is a non-local theory because it involves, just looking at the instantaneous distance between two objects which are far away, was replaced. And, people replaced it. And when they replaced it, they came up with a new theory, which I'll describe in a minute. But the new theory wasn't actually quantitatively very different. It couldn't have been quantitatively very different because, as I just explained to you, the Newtonian theory is a very successful theory, and it does give you very accurate predictions for many kinds of experiments and questions that you can ask. And so the new theory was an improvement, was only a small improvement in quantitative terms, but what one might call the ontology of the new theory, the philosophy of the new theory, was totally different. And the philosophy of the new theory, which was a philosophy that was engineered to ensure that physics is local, was that we shouldn't talk about the gravitational attraction between the sun and the Earth in terms of a force law, some force with which the sun attracts the Earth, but rather we should have this force or this effect being mediated by something else, and that something else turned out to be just the fabric of space-time. So this new theory stated that the way one should think about the attraction between the Earth and the sun was that we should think of both the Earth and the sun as living in some giant fabric of space-time, and in this giant fabric of space-time, the sun, by virtue of its mass, causes some bump in this fabric of space-time, and the Earth is now moving in this fabric of space-time. And the reason the Earth goes around in a certain orbit around the sun is not because the Earth feels some force from the sun, but because this orbit that the Earth is taking happens to be the natural orbit, or happens to be the natural trajectory in this bent fabric. So if this fabric was just completely flat, then the Earth would just fly off at some tangent. But because this fabric is being bent by the mass of the sun, the Earth happens to take some trajectory which happens to be the orbit. So you see, the words we are now using to describe the phenomena of the Earth going in an orbit around the sun are quite different. They're very different from the notion that the sun attracts the Earth with some force. But it turns out that quantitatively, if you were to compute the deviation in the orbit of the Earth due to these new phenomena, it's very small compared to the Newtonian dominant effect. Now, of course, these words I described are not just words, and it's important to remember that in physics, one never has just some words and pictures to describe something. There were some precise equations that people came up with to describe this. The equations were initially developed by Hilbert, and Einstein was also associated with them, even though it's called Einstein's Relativity. The equations were first written down by Hilbert. And the equations, you can understand, these are the equations actually, the ones I've written here. But there are some words which one can use to understand the equations. And the words are that matter tells space-time how to curve. So, in the case we were discussing of the sun and the Earth, the presence of the sun causes the space-time to curve. And that's the first equation here. On the left-hand side, you have something that involves the curvature of space. On the right-hand side, you have some matter. And then the space-time tells matter how to move. And that's the second equation that appears here, which is the fact that, which tells you that, that there's some, the space-time enters into this gradient here. And space-time tells matter how to move. And it's these two equations together that determine how the Earth goes in a trajectory around the sun. Okay? And as I said, these equations are, in a sense, give you a quantitative improvement over the Newtonian equations. But more than the quantitative improvement, they give you a slightly different philosophical perspective. And we can go back to the question that we asked. We can put back our giant who was moving the sun. But now the giant and the sun and the Earth are all living on the same fabric of space-time, right? They're living in this fabric of space-time. And now the way we describe what happens when the giant tries to move the sun is that it's not that the force between the Earth and the sun changes, but rather when the giant moves the sun, because the giant moved the sun and because the sun was causing this fabric to bend, when the sun was moved, that caused ripples to appear in this fabric of space-time. And these ripples propagate outward at the speed of light. So it's, as if you dropped a stone in a pond, and that stone in a pond causes some ripples to propagate outwards. And these ripples in space-time propagate outwards at the speed of light. And therefore, it takes 8 minutes for these ripples to go from the sun to the Earth, which is the same as the time it takes for light to go from the sun to the Earth. So if you think about this, if you think about dropping a stone in a pond, if you drop a stone in a pond, you will produce ripples that will move outwards. But if you have a boat somewhere else, if you have a small paper boat floating somewhere else in the pond, it will take time for those ripples to go from the place where you drop the stone and reach the boat. And it's only after that that the boat will know that something has changed and that you had dropped a stone. And so you see that this theory, this new theory, that's called general relativity, is an example of a local theory, where you make some change here, the giant makes some change near the sun here, and this causes only local effects, and it causes a ripple, and then the ripple also propagates locally. The ripple disturbs things around it, and these ripples slowly propagate, or not slowly, they propagate at the speed of light, but they propagate in a completely local way till they reach the Earth, and then the Earth knows that things have moved. And so, this theory of general relativity has this important property, which is called locality, which I want to emphasize. And in this way, it's philosophically completely different from the Newtonian theory of gravity. Okay. So now, of course, people had this theory of general relativity, and then they started to understand it better. Once you have a theory, of course, you might have invented the theory for some reason, but then you have to follow the theory where it leads you. And one of the things people found were that this theory had interesting solutions. For instance, the German mathematician Schwarzschild found this solution, which is a solution to those equations I wrote down. He was able to write down the solution. And I think, and this was, so just an interesting aside about Schwarzschild. When he wrote down these solutions, this was the time of the First World War. In fact, I think he died very soon afterwards because of the difficulties, because he was a soldier on the front lines in the First World War. And he might have written down many more interesting solutions if that had not happened. So just an aside that also to remember about the futility of war and how it takes away from science. But in any case, while Schwarzschild was involved in this First World War effort in Germany, he still had the time to work out this very interesting solution. And this solution has some very interesting properties. And the solution is called a black hole. So let me just try and describe the solution for you a little bit. Okay? So the solution that Schwarzschild found had the following property. If you went very far away, if you went very far away at asymptotic infinity, the solution looked a lot just like flat space, just like the space-time around us. But then there was some region in this solution, which is now called the event horizon, which had the property that, if you had an observer who fell into the event horizon, so this is this event horizon that you see out here, the observer would never be able to escape from that event horizon. And then the solution had an even stranger property. There was this region in the solution, which was a region of extremely strong gravity, which is now called the singularity at the center of the Schwarzschild black hole. Okay? So the solution looks like this. Now, and this is what's called a black hole solution. It's a solution to the equations I described previously, which has these properties that if you're far away from the black hole, things look a lot like ordinary space. And then somewhere in the middle, or there's this region which is called an event horizon, which has the property that once you've entered the event horizon, you cannot escape or exit the event horizon, and you're forced down, you're forced to fall into this singularity, and there in the singularity, everything gets crushed. Now, when the solution was found, people knew the solution, as I said, from the time of the First World War, but they didn't take it seriously because they felt, well, okay, this is some solution, but how do we know that this solution actually exists or has any relevance for nature? Because you might be able to write down some solutions to some equations, but that doesn't mean that nature necessarily realizes that system in the real world. But of course, since then, we have found a lot of evidence that these black holes, these solutions, which were found just as mathematical solutions to some theory, actually happen to have a real existence. So for instance, in our own galaxy, in the Milky Way, there's a gigantic black hole, which is called Sagittarius A star, in fact, for which the Nobel Prize was awarded some time ago, earlier this year. And this black hole is very big. It's 4 million times the mass of the sun, and it's very far away from us. So the sun is 8 light minutes away. This black hole is 26,000 light years away, and it's very far away from where we are. This is not the only black hole we know of. We know of lots and lots of black holes. For instance, this is a black hole that's in a completely different galaxy that's even more massive. It's 500 million times as massive as the sun, and even further away. Not all black holes have to be millions of times the mass of the sun. There are black holes which are much smaller. For instance, there is this black hole, which is called, by these strange naming conventions that astronomers have, which I never understand, which is called GRS 1915. And this black hole is here. This is an inset of this thing you see on top is an inset of this little square here. And this black hole it's in our galaxy, and it's much smaller than the black holes I showed you previously. It has only 14 times the mass of the sun. And the reason this black hole is very interesting is because this black hole has the property that it's spinning. And it's spinning about as fast as it could possibly spin. So, black holes, of course, have some mass, but they can also spin. They can turn around their own axis. And there's a limit to how fast they can turn around their own axis, which comes from the same kinds of limits that I described previously about how nothing can move faster than the speed of light. And so roughly one way to think about it is that the event horizon shouldn't be moving too fast. And that's, this black hole that we've observed is very close to that limit. So it's very close to being an extremal, what's called an extremal black hole. And so there are all kinds of black holes that we can see and we can see signals from. Of course, when I say see the black hole, you don't literally see the black hole because nothing comes out of the black hole, but you see emissions from around the black hole from matter that's falling into the black hole. And there are many interesting effects that you can use to detect those emissions. In fact, in the past few years, there's another observatory into the universe that has opened up. And that observatory comes just by looking at gravitational waves. So if you remember, I described in the example of the giant and the sun, how if the giant were to move the sun, it would cause ripples in the fabric of space-time. In fact, now using gravitational wave detectors, we can actually detect these ripples in this fabric of space-time. These ripples in the fabric of space-time are detected because you take these giant detectors. So you see a picture of this detector here, of this is called the LIGO detector. And when you have these ripples in the fabric of space-time, those ripples might cause this arm of the detector to contract or to stretch slightly differently from this arm of the detector, and that's what you observe. So these are very long detectors, and the shrinking is very small. But if you do very accurate experiments, then you can determine these ripples in the fabric of space-time, and you can use that to infer where these ripples came from. And that's one way people have learned also to observe black holes, which is a totally new dimension, totally new way of looking at black holes and detecting black holes. Now, these are very interesting questions. The questions of astrophysics, where you ask, questions about how you detect black holes, how do you see gravity waves, and so on. But the kind of stuff I work on is slightly different, and it has to do with black holes one might call vanilla flavored black holes, which are very simple black holes. So the black holes I was describing previously had the property that you could see them because they had all these masses and accretion disks around them, which led to radiation, which we could observe with our telescopes. Or maybe they collided with another black hole and we could see the ripples in the fabric of space-time that came out of that. But for theorists like me, we are interested in vanilla flavored black holes because there are already interesting theoretical questions one can ask about such black holes. So the kind of process that we like to think about often is, you just have some big ball of dust or some star which has lived out a full and happy life and has radiated away a lot of energy. And at some point, if the star is big enough, the star, it ends its life. It doesn't have any more energy to radiate anymore. And then it starts collapsing under its own gravitational weight. And once it starts collapsing under its own gravitational weight, it becomes smaller and smaller. And at some point, the star might cross its own event horizon. So it might become so small that it fits inside its own event horizon. And then nothing can stop it from contracting some more, and it keeps contracting till it becomes smaller and smaller and collapses into its own singularity. So this is a process which in a sense is a very simple process compared to the pictures I was showing you previously, because this universe I'm talking about has only this star which is collapsing and which is collapsing under its own weight to form a black hole. But as I'll try and describe, even this process leads to several interesting questions which I'll try and explain. Okay. I'm going to draw sometimes later in this talk these space-time diagrams which are useful to remember. So this process I described previously is sometimes called Oppenheimer-Schneider collapse. But in fact, there was an Indian physicist, B. Dutt, who worked it out a little earlier than Oppenheimer, and Schneider worked out very similar equations a little earlier. So it should rightly be called Dutt-Oppenheimer-Schneider collapse. And this is a diagram of this collapse of the black hole. The same diagram, the same cartoon that I showed you previously. But usually it's too tedious to keep drawing cartoons where you show one time slice and another time slice and a third time slice. So usually the way physicists do this is, they suppress one dimension, and this dimension on the x-axis is the radial dimension. And on the y-axis, instead of having space, we just have time. So the way you should see the propagation of time is just by moving up. So at the beginning, this was this black hole or this star, which was a big star. It was a giant respectable star. And then it started collapsing, and you can see the surface of the star becomes smaller as you go up with time. So time is moving forward as you go up on this figure. And at some point, it crosses the event horizon, which is this purple patch here. And once it crosses its event horizon, then nothing can stop the star from collapsing more, and it collapses into the singularity, which is here. And then the event horizon is now some region outside where there's no matter, and the star has just collapsed completely inside. So this is what's called a space-time diagram, which I'll draw maybe a couple more. Okay. So in fact, there's something. The space-time diagram is a nice diagram. But we also want to keep track a little bit about how light propagates. So let me just go back. In this diagram, as I explained to you, the event horizon is some region which light can't cross, but it's not clear from this diagram why light can't go from inside to outside. You see, you might have thought you shoot a ray of light and it would just go from inside to outside. And so there's a slightly different way to draw this diagram, which is called a Penrose diagram. Roger Penrose being the other person, in fact, who got the Nobel Prize earlier this year. And in that Penrose diagram, the property of the Penrose diagram is you rescale just your axis. So instead of drawing it in a one-to-one way, you rescale it in a certain way so that all light rays are always at 45 degrees. So this is a third picture of the same process that I showed you previously, where you have some star which is collapsing and collapsing into a singularity. Now the singularity is this curved line here, and the horizon is this 45-degree line here. And in fact, you see that the reason light can't cross the horizon is because the horizon is itself at the position of an expanding light shell. So, once a light ray crosses you, there is no way to ever catch up with the light ray. Even light can't catch up with another light ray once it has crossed you. And the reason it's not possible to cross the horizon is clear in this diagram. It's because the horizon, as I said, is itself the position of a light ray. And so if you shoot a beam of light here, it can't cross this other beam of light, which is this purple line here. Okay, but if you don't want to keep track of all of this, just remember that time is going up on the y-axis and space is going on the x-axis, and this is just depicting the same process where you had a star which was collapsing.
Okay. So a couple of questions regarding some of the things which you spoke earlier. Sure, so like I have 3 questions now. I'll post them one by one. So the first thing, how was the space-time fabric model conceived? Were there other models which were thought of and then dismissed?
Yeah. That's a good question. I mean, there were, of course, other models. There was a mathematician, Riemann, who thought about earlier ideas about how, you could formulate things. There was progress in mathematics about that time in a field called differential geometry, which precisely had to do with, how manifolds curved and so on. And then people realized that there was a property of gravity, which was an interesting property, which was called the equivalence principle, which was the fact that, if you drop like maybe gold and iron, they both get attracted at exactly the same rate to the earth, which is not true of other things like charge. Something might have like one kind of charge and some other thing might have another kind of charge. But it so happens that in gravity, if you're sitting in some gravitational field, whatever different kinds of atoms you have, they all fall at the same rate. And this is called and so people realized that maybe there was something intrinsic about gravity. Maybe you should try and describe gravitational attraction not in terms of masses being attracted, but in terms of something deeper or more fundamental. And so that's why they started thinking in terms of how to describe gravity in terms of something more fundamental, which was space itself. And before they thought of space-time fabric, they thought of spatial fabrics. And there was, as I said, progress in mathematics and differential geometry at the same time, which led people to think about these ideas. And then it was put together later by Hilbert and others into this picture of a space-time fabric. And so I don't know if that answers the question, but that's some picture of some of the things that happened. Yeah.
Okay. So as of now, another curious reader, is there any evidence which contradicts the current theory? I believe the answer to that is no.
That contradicts the current theory, meaning what? That contradicts what?
The space-time fabric one.
Oh, that contradicts general relativity? No, it depends on what you mean by that. There are some astrophysical observations, for instance, that we are not able to explain very well using general relativity. For instance, if you look at galactic rotation, it looks like there's some mass that we are not able to see. And so, usually people say that, well, there's some dark matter that you're not seeing in the galaxy. And so the visible mass that you're seeing is not sufficient to explain the galactic rotation curves, but there might be some other mass that you're not seeing, which is why the galactic rotation curves are consistent with general relativity. But on the other hand, it could be that maybe the theory of gravity that you have is wrong and the mass you're seeing is all there is, and there's no such thing as dark matter. So, I mean, there are of course many puzzles that we see around us. We do believe that general relativity is accurate, and there's certainly been no place where it's been falsified conclusively.
There seems to be a technical issue. We'll get back as soon as possible. Sorry for the delay.
Hello, sorry, there's some connectivity problem.
Yes, we can hear you now.
Sorry, did some internet connection went down?
Yeah, but maybe like the last 15 seconds we lost you. That was it.
Okay. Anyway, I was just saying that there are these issues of dark matter. I don't know where so I was giving an example of cases like these galactic rotation curves where we are not able to explain the rotation of some stars using the matter that we see, and we usually explain that away by postulating some issue with the matter that we see. We say there's additional dark matter that we are not able to see. But of course, it could be maybe that there is some other issue, and there's some issue with the theory of gravity.
Okay.
Can you see my screen, or you can't see my screen?
No, your screen sharing has stopped.
Yeah. Okay.
Yeah, perfect.
Yeah. Just 1 second.
Yeah. And once again, the annotations, please.
Yeah, go on. There's a third question, so you can go on and ask the question. Yeah.
Yeah. So you were mentioning about a black hole spinning. So another question relating to that. So can a black hole not stop spinning, or can a black hole stop spinning? If it did, will there be any change in the properties of the black hole?
Yeah, it could lose. Generally black holes tend to gain angular momentum, but yeah, you could try and stop a black hole from spinning, and there would be changes in the property. These spinning black holes have this region where where you're forced to be dragged along with the black hole. It's called an ergosphere, and if the black hole stops spinning, that ergosphere would go away. So yeah, a black hole could. I mean, it's a theoretically allowed process where you could lose this angular momentum. But I mean, this is a different question from whether it's astrophysically a plausible thing, but it's a theoretically allowed process.
Sir, why spin? Why spin black hole? Energy force were given.
I can't hear you now, Niranjan.
We really prefer if you all of you type the questions in the chat instead of unmuting yourself. In that way, there'll be less clutter. Thank you. So yeah, thank you. So we'll take up maybe the other questions. There are a few questions. We'll take it up towards the end.
Okay, fine.
Thank you.
So I'll go on then.
Yeah.
Okay. So so now people realized, after they'd investigated and understood these properties of black holes that I described previously, our giant has made a reappearance. That you could do experiments with black holes. So let's say you had this black hole, and our friendly giant, who was pushing the sun around, now decided to do something more dramatic. So this giant took the sun, or maybe took the Earth, this blue Earth, and decided to throw the Earth into the black hole. Okay? So it was a big black hole, maybe this big black hole that I was describing previously, the Sagittarius A star, and someone came and pushed some additional matter into the black hole. So this is an allowed process, right? In fact, it's a process that happens all the time, where you have some black hole which has already been formed, and then some additional matter is falls into the black hole. So I described earlier this vanilla black hole where you had some star which collapsed, but now I'm introducing a little bit more additional stuff, where there's some additional matter that falls into the black hole after the black hole has been formed. So one could, draw the same process. Of course, we don't want to draw giants and so on in serious physical discussions, and so one can draw the same process on a space-time diagram. And this is the same diagram I showed you previously, where you have the star which has collapsed, and here's this additional matter that's going from outside the black hole, and as I remember, the time goes up and it's falling into the black hole till it also goes and falls into the singularity. Okay? So when this happens, the black hole becomes a little bigger. So this matter falls into the black hole, and then the black hole becomes a little bigger from what it was previously. And so the horizon grows. And in fact, physicists found that there were some equations that you could use to describe how the horizon grows. And these equations were very similar to some equations that many of you have seen, which are the equations of thermodynamics. And physicists found that, in fact, the simple black holes that I described previously, which were just formed from collapse, obeyed, if you started doing these things where you threw in some additional mass, like this mass dm, then what would happen is, sorry, what's happening? Yeah, what would happen is that the area of the horizon would change a little bit. So the mass increased, and then the area would increase a little bit, and there would be some constant of proportionality between them. And then there are other things you could do. In fact, somebody mentioned what happened if you change the angular momentum of the black hole. And there are other terms you could add, all of which, would, so there's some equation you can write down which says dm is kappa times dA plus the angular velocity times, the angular momentum, and so on. You can write down other kinds of terms of this kind, which are work terms. And people realize that these are very similar to the terms that appear also in ordinary thermodynamical systems, where if you try and change the internal energy of some object, there's some change in the entropy, and you should multiply that with the temperature. And then there are work terms, which are like a PdV kind of terms, which you often see when you study thermodynamics. But there's a second analogy between black holes and thermodynamics, which is that, in thermodynamical systems, we know there's a second law of thermodynamics, which tells us that the entropy always increases. And similarly, for black holes, people found, in fact, somebody asked previously about these black holes which are spinning. It can happen sometimes that for a black hole, the mass of a black hole decreases, but people found that the area of the black hole would never decrease. So the area would always increase. And that is analogous to the second law of thermodynamics. So people found if you take these idealized black holes and then you start doing these thought experiments where you throw stuff into the black hole and you ask how does the mass of the black hole change, how does the area of the horizon change, and so on, people found that there were these laws you could write down for those changes, which are given on the right hand side, which were an analogy with the laws of thermodynamics. Now, this is not such an uncommon situation in physics. This is not such an uncommon situation in physics because it very often happens that two different physical systems obey the same physical equations. Those of you who studied the simple harmonic oscillator and have studied also, LC circuits, know that the simple harmonic oscillator obeys the same equations that an LC circuit does. A damped harmonic oscillator obeys the same equations that an LRC circuit does. Okay, and indeed those equations are the same. If you read Feynman's lectures on physics, you will find there's an entire chapter on the same equations have the same solutions. And so this is indeed something that happens often in other cases in physics, but that doesn't actually necessarily mean that the systems are the same. A simple harmonic oscillator is not an LC circuit. A simple harmonic oscillator, a mass on a spring is a mass on a spring, but a mass on a spring might obey the same equations as an LC circuit, but a mass on a spring is distinct from an LC circuit, and that distinction might be important. Now, one of the discoveries that was made is that, so this is what I was saying about black holes being the same as thermodynamics and these two systems obeying the same equations. But one of the discoveries that was made was at about that time and was made by Hawking, by Stephen Hawking, whom you might have heard of, is that this analogy is not formal. In fact, the black hole really does have a temperature, and you should really think about it as a thermodynamic object. And the fact that the black hole is obeying these laws, which look like the laws of thermodynamics, is because the black hole really is a thermodynamic object. And Hawking's discovery was that when you add quantum effects to a black hole, you actually, it's like starting what one might call a fire at the horizon that burns with a certain temperature. And that temperature for simple black holes turns out to be just inversely proportional to the mass. And there are various other constants that appear here. This constant is called h bar. This c is the speed of light. This is Boltzmann's constant. This is Newton's constant. And so there are various other constants that appear here. But all, the only constant that depends on the black hole in this equation is this mass, is the inverse proportionality of the mass. And people found that quantum effects cause the black hole to actually emit radiation with this temperature. So the black hole, when you add quantum mechanics, is not really a black hole, but rather it's a black hole which is emitting some radiation at this temperature. Okay, there are physical ways to think about this, and this radiation is called Hawking radiation. In fact, it's not been observed because it's I'll explain why, but it's theoretically very well founded. And the way to think about this Hawking radiation is that you should think that in quantum mechanics there are always fluctuations that occur even in the vacuum. And so what happens is that near the horizon of the black hole, this purple line that we've been discussing, there is spontaneous pair creation. And if this pair creation, one particle streams out and the other particle falls in. And it's these effects, if you have an observer who's just outside, that observer just observes this particle which is coming out and doesn't observe the particle which went in. And so these spontaneous fluctuations look like they lead to a stream of radiation that's coming out from the black hole. Okay. Now, once again, these effects are very weak, and I'll explain how weak they are. But once again, since we're talking about philosophical issues and since we're talking about pictures, this changes the picture that one might have for a black hole. Earlier I was drawing a black hole with this event horizon, and there was this region far away that looked like ordinary space, and there was this event horizon where an observer could fall through. But now it turns out there's something slightly different. If you look at this black hole from far away, it doesn't look exactly like a black object, but it looks like there's some radiation which is coming out here, which is this yellow radiation which I've plotted. I should emphasize that if you're an observer who's just falling into the black hole, if you're just freely falling in, you won't see this. You'll just cross this radiation and you won't feel it at all. It'll just look like you're falling through empty space. But if you're someone who's far away, you can observe this radiation that's coming out. and that's this radiation that's displayed here. Okay, you can in fact compute more than just the temperature of the black hole. You can compute the entire spectrum of emission from the black hole, and the spectrum obeys something called the Planck's law, which is the spectrum of emission from other kinds of black bodies that you see as well. Now, if you take a black body and you heat it up, the black body always radiates with some, it radiates in different frequencies. It radiates dominantly at the frequency which corresponds to the temperature of the body, but it also emits some radiation at much higher frequencies and at much lower frequencies. And this characteristic curve is called the Planck curve. And it turns out that these black holes also obey the same curve. So they emit radiation with a certain frequency, which obeys the same black body distribution as other black bodies do. Okay, so black holes in some sense are this black body name came from really looking at black bodies, not by looking at black holes, but black holes do behave like black bodies in terms of the radiation that they give out. So they radiate, you can compute that entire curve, and that curve is different for different temperatures. This blue and brown curve indicates different temperatures, but the temperature is the only parameter that controls the entire curve. Okay. So now you could take this forward, and you could ask the following question. You see, the black hole has some energy, right? And that energy, I'm sure all of you have heard of the formula E is equal to mc squared. So if the black hole has some mass, there's some energy that corresponds to that, which is just the mass into the square of the speed of light. But I've been telling you that this black hole is emitting radiation, and so there's some rate at which the energy is being lost from this black hole, just like energy is being lost when you have some other fire that burns. And in fact, I'm sure some of you have also studied the rate at which the energy is lost, and that's given by what's called the Stephen-Boltzmann law. The Stephen-Boltzmann law tells you there's some constant sigma, and then you have to multiply it with the power of t to the 4, and then you multiply the area of the body that's emitting. And so it turns out that the energy is lost due to radiation with the sigma t to the power 4a law, which is the same law that other black bodies obey. But if that's the case, then that means that the mass of the black hole must also be decreasing due to this radiation. And so that tells you that you can write down a simple differential equation for the rate at which the mass increases. The reason it's a simple differential equation is that, remember, I told you that the temperature was also proportional to 1 over the mass. It turns out the area is proportional to the square of the mass. So it turns out that the rate of change of the mass is just given by 1 over the mass square. There's a minus sign missing actually in the second equation here. But the rate of change of the mass is just inversely proportional to 1 over the mass square. Okay? And this equation just follows by putting together simple thermodynamics with the formula I gave you previously for the temperature of the black hole. Now, if this is the case, then this would mean that after some time, all the mass of the black hole would be lost. And you can compute the lifetime just by solving the differential equation I showed you previously. And you'll see that the lifetime is proportional to the cube of the mass. Okay? And that's because the equation looks like dm by dt is minus 1 over m squared. And you can compute how much time it takes with some starting mass for m to go to 0. And that turns out to be the cube of the starting mass. And I've put in some this is the mass in kilograms. So mass by kilogram cube, and this is multiplied with seconds. Okay? So this is the lifetime of the black hole. And just, this tells us that if you just follow your nose, remember, as we were doing also when we looked at the Schwarzschild solution and other cases, we have some theory, it tells us some things, and now we're just following our nose and following where the theory tells us. It tells us that the black hole will evaporate completely in this time. Now, there's a reason why these, I said Hawking radiation and all of these other effects have not been observed. And that's because, if you were to ask for what is the lifetime of a solar mass black hole, if you just put in the numbers in the formula I gave you previously, you would find that if you had a black hole with the mass of our sun, the lifetime of this black hole would be 10 to the 67 years, okay? Which is much, much, much longer than the known age of the universe. Okay? So a solar mass black hole is effectively eternal, and these effects are not of any relevance for a solar mass black hole. These effects might be of relevance if, at some point in the future, we can create or we can observe black holes which have a much smaller mass. So for instance, if you were to take a black hole with a mass of a big plane, okay, so like 400 tons, then the lifetime of that black hole would only be 5 seconds. So people often ask about the Bermuda Triangle, which is people say is a black hole which eats up planes. So the point about, one reason why the Bermuda Triangle can't have a black hole that eats up planes is if the Bermuda Triangle was a black hole of this right size to eat up planes, it would actually evaporate off pretty fast, and it would very soon cease to exist. Okay? So, if you take black holes or if you take like this building and you shrink it into a black hole, which of course we can't do with current technology, then indeed this lifetime would be relevant, and it would be much smaller, and it would correspond to time periods that we're familiar with. Okay? But these lifetimes are not relevant for astrophysical black holes, but they're theoretically relevant because there's nothing that prevents a black hole of this size from existing. Okay. So now, we follow our nose a little bit more, and we see that let's say you were to wait for a long time, or let's say you were to have a star which was, or not a star, or some object, like some plane or some other smaller mass which was to collapse and form a black hole. Then you see, I've told you about two processes. I told you that the star, or some other object, if you squeezed it with enough pressure, could collapse to form a black hole. But once it collapsed to form a black hole, there would be quantum effects that would start a fire around this black hole. And this fire would eventually, if you waited long enough, cause the black hole to entirely burn up and just evaporate into this thermal radiation with the spectrum that you see on the right-hand side. Okay. Now, if you think about this a little bit more, you will see that there's something a little puzzling about it. Okay? And the thing that's puzzling about it is that the radiation that I showed you, remember I showed you this radiation, and I told you that the only characteristic of this radiation was the temperature. Okay, so it was governed by one parameter, which was the temperature. But if you think about this, you see the star itself, the details of the initial star are governed by much more than one parameter. One could take the library of this institute and throw it into the star, and that would have some information in it. And what we seem to be finding here is that you could take one star of one kind and another star of another kind, and collapse this star into a black hole, and collapse the second star into a black hole. And then both these black holes, would evaporate into radiation. But it looks like if the stars had the same mass, then the radiation at the end would be the same. That doesn't make, and that would suggest that this time evolution, which is, the star going into radiation, cannot be reversed, because with the final radiation, you can't go back and back calculate what the star was, because the radiation looked like it just depends on the temperature and not on many other details of what made up the star, the density of the star, or whether the star was made of gold, or whether the star had more iron or less iron or more metals, or whether it had a library or whatever else. Right? It looks like the radiation that comes out just depends on the temperature. And so it looks like the time evolution arrows cannot be reversed. Now, the point is that this is actually in contradiction with a very venerable principle of physics, which all of you are familiar with, which is the fact that time evolution can always be reversed. You've already studied this when you look at just the behavior of balls or behavior of cannonballs. If you're given a cannonball, and the kinds of questions one is often asked is, if one shoots a ball with some initial velocity at some angle, where will the ball end up? But in fact, you can ask the opposite kind of question. You can say, if a ball landed at some angle with some velocity, where did the ball start from? And indeed, when they do these kinds of ballistics research, when there's some crime scene, this is exactly the kind of question they ask, right? They ask, here's a bullet which came with some and embedded itself in a wall from this angle. So where could it have been fired from? And so, in fact, physics tells you that not only can you solve the equations of physics forward in time, you can always solve them backward in time as well. And this is a property not only of classical physics, which is that, the rate of change of momentum is some force, but it's also a property of quantum mechanics, which is governed by the Schrodinger equation, which can also be solved forward in time or backward in time. And so physics has this property of being reversible, that the evolution of time is always reversible. And it looks like black holes and the phenomena that we described previously do not obey this property. Okay. Now, so that's what's sometimes called the information paradox. Okay, it's the fact that black holes look like they don't obey this property of reversibility. And this, in fact, is the puzzle that the central puzzle I wanted to describe. In fact, this might be a good time to pause for some questions, and then I'll try and explain some ideas for the resolution of the puzzle. Are there any questions right now?
I think the questions are more or less a bit general. Maybe it'll be nicer if we can take it towards the end as of now.
Okay, fine. Okay, so now what's the answer to this? Okay, so it turns out the answer to this, which I think we understand, is that the answer to this is that if you had a black hole, this is a cartoon, and the black hole is emitted like radiation. I've drawn these radiation, so you should, that's because the radiation can be photons and gravitons, and the photons can have different color because they can have different frequencies. So let's say you have a black hole which has emitted a lot of radiation, and it looks like this radiation is completely thermal. But in fact, remember that when I told you about black bodies and them emitting thermal radiation, you could have asked the same question there. You could have said, this black body that I had had some details, right? It had some microscopic details of the fact that one part of the black body was made of some kind of atoms, or the black body was made of some other kinds of atoms. So there were all sorts of details that go also into a black body. A black body is not really just some featureless black body. And you could have asked, where did all those details go in this radiation that's being emitted? And in fact, what we are seeing here is the same kind of question happening about black holes. So, it looks like a black hole emits like photons, and the only characteristic, this is some random distribution of photons, which is only characterized by the temperature, right? So there's some number of blue photons, some number of violet photons, some number of red and yellow photons, and that proportion is governed by the temperature. And it looks, other than that, they've just been emitted randomly. But in fact, if you look more closely, that's not really the case. And this is always the answer to questions of the seeming lack of time reversal in physics. This kind of question of the lack of reversibility is a question you can in fact ask for other cases. You could take a ball and roll it in the ground, and after some time, the ball would come to a stop. And it would look like the ball has lost information about the initial speed with which the ball was rolled, or the initial position from where the ball came from. And the answer to this question, the reason this is not a contradiction, is because in fact that information is not lost, but rather it has gone into some very small delicate correlations of the ball and the different atoms on the ground and so on, so that information has dissipated from being easily accessible to us to being very hard to access, because it went away into some very delicate effects when the ball stopped and the way it affected the ground around us. But if you could keep track of all of those delicate effects, you would be able to back calculate where the ball came from. And it turns out that the same thing is happening with black holes, and that when you look at these black holes, you look at this radiation that's emitted, there are in fact delicate correlations in this radiation that's being emitted. So in this cartoon, in fact, there are also correlations, which is that whenever there's a red dot, you wouldn't see it at first sight, but this cartoon has some correlations, which is whenever there's a red dot, if you draw a line to the black hole and to the other side, you'll find a blue dot at exactly the same distance. And whenever there's a purple dot, you draw a line to the black hole and to the other side, you'll find a yellow dot exactly diametrically opposite. And so this is just an example of, this is not the way real correlations in a black hole work, but this is an example of how some radiation or some stuff that looks random at first sight and looks like it doesn't contain any information might actually contain information which corresponds to correlations between different random elements, which is not visible at first sight, but is only visible when you observe things very carefully. And we believe that this is in fact the answer to why black hole evolution looks non-time reversible. It's because it is actually time reversible, but rather what has happened is that the information that was easily accessible in the star initially has now gone off and is now hard to access in the final radiation that's emitted. Okay. Now, how hard does it have to be to access? How small can these correlations be? So you can in fact compute how small these correlations can be. And it turns out these correlations can be suppressed by exponentially in a parameter called the entropy of the black hole. So remember, I told you in the beginning that the black hole had a temperature. It's a thermodynamic object. It also has an entropy, which in fact I already mentioned was proportional to the area. This entropy is in fact area over 4 multiplied with some fundamental constants. You see once again the speed of light and h bar and Newton's constant. And if you write in SI units, it looks like this. But it turns out these correlations can be exponentially suppressed. So this is e to the minus s. So they can be very, very small and still preserve information about the final state. Okay? And so these entropies can be extremely, extremely large for something like the sun. If you were to put in the mass of the sun here, that's 2 into 10 to the power 30, you would find 10 to the power 77 appearing on the right hand side. And what we're talking about here is e to the power minus 10 to the power 77. Okay? So even if you have very small correlations in this radiation that's emitted from the black hole, these are enough to preserve the information. And in fact, in the calculation that Hawking did to compute the spectrum, he did not keep track of these very small correlations. And we believe that if you were to keep track of these small correlations, you would be able to recover the information that fell into the black hole. Of course, one could still ask, one could ask a slightly deeper question. One could ask, Well, you have this black hole, and I explained to you right now that if you had very small correlations in this Hawking radiation, these correlations could preserve information about the matter. But if you remember some of the diagrams I showed you earlier, you had some star that was collapsing, and then there was this horizon which was far away, and this horizon was far away from the star that had collapsed. And so you could ask this black hole radiation, which looks like it's coming from the horizon, how does it have even a small amount of information about this matter that fell in? And this, in fact, is a more interesting question than just asking the question about how is information preserved and it lives in small correlations. You can ask, how are these correlations actually formed? Okay? So it turns out that there's an interesting story there, which has to do with interesting effects in gravity, which I'll now try and explain. So the next slides might be maybe hard to understand for some of you, but might be interesting for some others who are interested in quantum mechanics. So you see, we usually draw these stars and we draw these localized objects, right? We, in classical physics, we think of a ball which is just sitting at one place and it's just localized in that place. But in fact, those of you who studied quantum mechanics and those of you who studied maybe also some combination of relativity and quantum mechanics, know that things are not that simple in quantum mechanics. And that's because if you think of objects which have a definite energy, okay, or objects which have a definite momentum, then such objects in quantum mechanics do not have a definite position. Okay? So objects which have a definite momentum do not have a definite position. And in fact, they're completely delocalized in quantum mechanics. This is a consequence of what's called the Heisenberg uncertainty principle, which tells us if you ascribe a definite energy to some object, it doesn't have a definite position. If you ascribe a definite momentum to some object, it doesn't have a definite position. Okay? So if you look at something which has an exact energy, it doesn't have exact position. Now, so that means that something which has an exact position doesn't have an exact energy. So if you want some object in quantum mechanics which is localized, you can build a wave packet by superposing some of these waves corresponding to different energies. Okay? So those of you who studied quantum mechanics will know this. But for those of you who've not, what is important to realize is that in quantum mechanics, whenever you try and think of some object which is localized, or, maybe us as human beings who are localized in one place, that's because we are made up of a superposition of many different waves which have different energies, and that superposition sticks together in the form of a wave packet. But it's important that it's a superposition and not just some exact energy or momentum eigenstate. So usually the way we build up some kind of superposition is by taking some energy eigenstate, so that there's some eigenstate of matter, and just adding it together with some coefficients ai. But now it turns out in a theory of gravity, there's something funny. There's some additional feature that happens. And the additional feature is that, there's a Gauss law in gravity. The Gauss law tells you that if you're far away, and just by measuring the gravitational field far away, you can determine the energy. And therefore, if you try and construct a localized state in gravity, the way one constructs a localized state in ordinary quantum mechanics, then you would have thought, if you forget about the second part of this equation, you would have thought that you would just take a superposition of different momentum or energy eigenstates and build up some wave packet that's localized. But you can't do that in gravity because you have to keep track of the energy, and the energy is available from far away. If you have some localized object here, you can always measure its energy from far away. And in fact, the energy has to be correlated, the energy as measured with the metric, which is available here, or as measured by the gravitational field, which is measurable far away, has to be correlated with the energy of the object. And so you see that if you try to construct the best approximation you can to a localized excitation, that best approximation involves a sum of terms where this object here has some energy, and the gravitational field far away also tells you about the energy. Okay? But this gravitational field is something you can measure far away, and the joint probability distribution of measuring the gravitational field and this other material, in fact, can tell you everything about this lump of matter in the middle. Okay, so this is something that's maybe not so hard, that's hard to explain without writing down many more equations. But the punchline is that because in a theory of gravity, you have to keep track of the energy, and the energy can be measured far away because gravitational theories have this feature called the Gauss law, which allows you to measure the energy far away. And because energy eigenstates are not localized objects, you cannot construct a localized excitation in quantum gravity the way one constructs a localized excitation in ordinary quantum mechanics. and the fact that you can measure the energy and correlate it with other kinds of observations far away, in fact, allows an observer making measurements on this far away sphere to completely determine the state of what's happening inside the sphere. Okay? And so this is actually the resolution to this puzzle I was explaining about how these correlations are formed. In fact, this leads to a broader principle that one can call the holography of information, which is the principle that, on the same diagram that I was showing you, if you take like some degrees of freedom or some excitation that lives somewhere here in space, then at the same time, by making observations far away on these red dots, you can reconstruct what is happening here. Okay? And that happens because of these features that I described somewhat imprecisely in the previous slide, but it's a broader feature which is called holography, which appears in theories of gravity. Okay. So this actually tells you how these correlations are formed. It tells you that even though you thought that the star had collapsed and had become smaller, that was just some classical picture. In fact, there is some information about the star that is always available here near the horizon. And it is this information that can be recovered and that affects the Hawking radiation that's going out. And it is for this reason that the information about the star here is able to exit the black hole, and you can form these small correlations which preserve information about what made up the black hole in the first place. Okay. And this arises, as I said, because of this more general principle in quantum gravity, which is that information about some stuff or some events that are happening here can also be accessed by making measurements around on a large sphere that surrounds this event without actually probing what's happening here. So this resolves, in a sense, this information paradox. But you see, it brings us back, in a sense, a little bit back to where we started from in the beginning, because it tells us that now in quantum mechanics, we should think about gravity in a slightly different way. Earlier I told you there was this fabric of space-time, and in this fabric of space-time, if you made some bumps here or you made some disturbance here, this disturbance would travel only at the speed of light. But now I'm telling you that, it's not possible to make a disturbance here without affecting some things far away. Okay. So there's another picture that's sometimes used. It's only a cartoon, but the picture that's sometimes used to describe this is that instead of thinking of a fabric of space-time, you should think of threads of space-time. And so, if you wanted to make some excitation or you wanted to change something here, what these threads of space-time tell you is that you also have to change something far away. And there's no way to change something in the middle of this fabric without changing something far away. And for this reason, information is not localized in quantum gravity, but is always in some essential way delocalized, so that you can read off what is happening in the middle by looking at what's happening in these threads that are far away. So it's kind of interesting because, in a sense, we've moved back to where we started from. So I started the story by describing, something about Newtonian gravity. And I said Newtonian gravity was a very successful theory which described the sun acting instantaneously with a force on the earth. And then I said, well, we didn't like that so much. We didn't like the fact that Newtonian gravity had these non-local features where the sun acts instantaneously on the earth. And so we changed the ontology of the theory, and we invented the fabric of space-time, which led to only local propagation, where you could make some excitation here, and that excitation would only propagate at the speed of light. But then we investigated that theory some more, and we found this theory had black holes. And then we found some puzzles that had to do with black holes. We invented, after all, the fabric of space-time also because of a puzzle with Newtonian gravity. But now we investigated this some more, and we found some more puzzles that have to do with black holes. And now the way we resolve these puzzles is by changing the ontology once again and saying, rather than this fabric of space-time, we have these threads of space-time. So things are not exactly local. Information in one part is not really independent of information in other parts. And so it looks like we've progressed, or in some sense, or maybe gone back a little bit once more. And that's an interesting story about how, the perspectives on gravity and on space-time have been changing. Okay, so I'm sure there are many questions. I'll stop here and we can take questions.
Thank you very much. So to start off with, this was indeed like an exceptionally well presented. So
I can't hear you clearly. Could you speak a little closer to mic? Yeah.
Yeah. Can you hear me now?
Yeah, now I can hear you. Yeah.
Okay, perfect. So I was saying like thank you very much for this wonderfully presented session. So I'm sure like you've got quite a few minds wondering. So we've received quite a few questions already. So I'll just post them to you one by one.
Okay.
So you were talking about the lifetime of a black hole and gave an expression for it. So what happens after the lifetime of a black hole? Is there anything to it?
So, there's a question of what happens at the end of a black hole, but in the picture I was describing was that the black hole evaporates into gravitons and photons and other kinds of particles, and so the black hole ceases to exist. It's just evaporated into a gas of radiation. So,
Okay.
The black hole ceases to exist. If you were to take a black hole, if you were to form like one of these small black holes, then the black hole would emit radiation and it would explode into this gas of radiation, and it would cease to exist. It would just be radiation that would be left.
Okay. And I've got quite a few questions about what exactly is information. So what do you
Could
mean
you hold the
when
mic closer to your? I can't hear you.
Sorry.
Yeah.
What exactly do you mean when information is lost? So what is the information?
Yeah, the information, you see, if you start with some initial state, the final state should always have details about the initial state. The principle of physics is that, if you start with initial state, given the final state, you can back calculate the initial state. Now, in the initial calculation that Hawking did, it looked like, if you started with a black hole, when you say information, it just means details of the initial state. That's information. So details of the initial state could involve some book that was thrown in, but it could just be some, some features, the fact that, the star was more dense in one region and less dense in another region. So the full details of the initial state constitute information. And in this process, in this calculation that Hawking first did, it looked like the black hole, evaporates, and you have this gas of radiation, and the gas of radiation is entirely characterized by one number, which is the temperature, which is clearly not enough to keep track of all the details of the initial state, the wiggles in the density or any other features that the star had. And so it looks like information about the initial state is lost, which means that from the final state, which is characterized only by the temperature, one cannot back calculate the initial state. So that's what one means by a puzzle about the reversibility of time.
Oh, wow. Okay. That made it extremely clear. Thank you. And yet another question relating to the spin of a black hole. So why does a black hole spin? So is a black hole in some sense born spinning, or does it gain a spinning characteristic later?
You have to conserve angular momentum. So if the star that formed it was spinning in the first place, the black hole that's formed will also be spinning. But even if the star that formed it wasn't spinning and you threw in some stuff which had angular momentum, you have to conserve angular momentum. So the black hole would have to pick up some spin. So the black hole just spins the way other objects spin. You have to have conservation of angular momentum. So you throw in something with angular momentum, and now the black hole has angular momentum.
Okay, thank you. So I think these are all the questions I see as of now.
So I can't hear you once again if you put the mic down. Yeah.
Oh, okay. I'm extremely sorry for that. So yeah, I guess these are the questions we have as of now. If
Sir, I actually have a question. Sir, am I audible?
Yeah, I can hear you.
So my question is, you said that when the radiation comes out, there's a certain correlation between the various factors and the radiation which comes out at a particular time.
Right.
Now, whenever we back construct a data, this correlation is definitely not equal to 1. It's some value between 0 and 1. Whenever we back calculate a data from a correlation between 0 and 1, we get some errors, like we cannot construct the exact initial data. Then how is it possible? Because
no. So sorry, when I meant correlation, I meant that the information in the radiation is not just the temperature, it's also a whole set of other probability distributions which have to do with the joint probability distribution. So if you just looked at the probability distribution of one photon, what's the color? That's given by the temperature. But then there's a lot more information in the joint probability distributions of different photons that have been emitted. So when I said correlations, I meant these joint probability distributions. And when I said information is preserved, it's the fact that the information initially, which had to do with all these, as I said, these density distributions and so on, is preserved later in these joint probability distributions of these observations you can make at later times. So correlations just means that the joint probability distribution also has some numbers. It has information associated with it, just the same way as a density profile does. And what this process of black hole evaporation and radiation does, of black hole formation and evaporation does, is it converts information from maybe some information about the density profile or some other way you had of characterizing the initial state into information now about these joint probability distributions of observations you can make in this radiation. Does that answer the question?
Yes, sir. Yes, thank you so much, sir.
Okay.
Yeah. There's one more question which just came up. So does only mass and radius cause an object to be a black hole, or is there something more other? Is there another characteristic which a black hole for which a black hole is required?
Well, I'm not sure what the question is, but if you were to take a certain mass and you were to squeeze it inside its Schwarzschild radius, then that's a black hole. I mean, this formula for the Schwarzschild radius is more complicated in the presence of angular momentum and charge and so on. But if you just think of an object with mass and you put it inside a sphere which is smaller than the Schwarzschild radius, that becomes a black hole. That's the characteristic of a black hole is an event horizon. It's that there's this region of no return, where if something falls in, something can't come out. And so the characteristic, the really defining characteristic, is that of an event horizon. But if you do take some mass and you squeeze it into its Schwarzschild radius, it does form a black hole.
Okay, and there was one more question. Yeah. So what is the difference between an event horizon and a trapped surface?
Okay, so the event horizon is a these are some okay. This so the event horizon is a global property of the spacetime. Okay, so when we talk about an event horizon, we are talking about we are talking about some global causal properties, and that there's some notion of asymptotic infinity, and there's a question about whether some observer can go from one region into the asymptotic region or not. Okay, so the event horizon is some global object that we talk about. This is a subtle question that someone has asked, but you can talk about local properties. You can ask, if you have rays of light, do all shells of light expand, or do all shell? So usually what happens is, if you just take some point in space here, you can have an expanding shell of light and you can have a contracting shell of light. It could happen, and this does happen, if you're sitting just behind the event horizon, that all shells of light contract. If you start a shell of light inside the black hole, it always contracts towards the singularity. So that's something you can just see locally. So there's a question of whether something is a local measurable or whether something depends on global properties of the space-time. The event horizon is something that depends on global properties. But these issues, these subtleties were not relevant for what I discussed today.
Okay. A curious reader wants to know are there any misconceptions or unanswered questions about black holes?
And there are many misconceptions and unanswered questions. There are many. I mean, it would take too long to. Well, first of all, misconceptions are infinite, but there are also many unanswered questions about black holes. There are many things we don't understand. We don't really understand this issue of well, there are many astrophysical questions about black holes that are open. The kinds of questions I was describing for the majority of the talk are just simple theoretical questions about black holes. You take some very vanilla black hole and you ask some simple theoretical questions, and even there are many very interesting questions which are not answered. Even this question of I said black holes are thermodynamic objects, but you could ask when we say the air is a thermodynamic object, we have some kinetic description of the air in terms of atoms, and you could ask, for black holes in our world, what are the atoms that make up the black hole? What are the ultimate degrees of freedom that describe the black hole? And we don't know that, and there are many other puzzles about black holes that are unanswered. So there are theoretical questions just about these vanilla black holes that are unanswered, but there are also many questions about astrophysical black holes which are also unanswered. How black holes behave, the black holes that we can see, and so there are a very wide variety of questions about black holes which have not been answered, both theoretically and astrophysically.
Okay, thank you. And another question relating to when you were speaking about LIGO. So what is the future objective of LIGO now that gravitational waves have been discovered?
Well, it's a new way to observe the universe, right? So I mean, it's like a telescope which is allowing us to make observations in a spectrum that was previously not accessible to us. Earlier we had optical telescopes. Okay, we had radio telescopes. They allowed us to see different things. Now you can see things using gravitational waves. So it's a new window on the universe in a sense. It's not just to observe one black hole collision. It's the fact that we learn about new astrophysical events that we could not have seen otherwise.
Thank you. I think these are all the questions I have. So I'll wait for a minute. Please type out your questions completely in the chat if there are any, and if none, we can come to the conclusion of the session.
Sir, am I audible?
Yeah, I can hear you. Yeah.
Yes.
Sir, what is exactly mass? Like, what do we understand as it? Like when we say mass, what is it actually?
Well, So I'm not sure what level the question is asked, but when we discuss the mass of black holes, we actually define it using the Gauss law. So you go far away and you observe the deviations. This diagram that you have here is some bump that was caused by some mass. So in fact, the way you define mass and gravity is you go far away and you observe the deviations from flat space-time, and those deviations are used as a definition of energy or definition of mass. And that's in fact there are other local definitions of energy that we usually use, but in the theory of gravity, the best definition of energy is actually the global definition. You just go far away and you observe the deviation from flat space-time that's caused by some object, and that's the mass.
Okay, sir. Sir, could you suggest some nice books to understand the topic very well?
You will have to do a PhD. So I mean, these are subtle issues. So these are I don't know of any good popular book that will help you understand the topic well. There are many popular lectures and so on that you'll find, but if you really wanted to understand things carefully, I mean, you would have to study some amount of general relativity and some amount of quantum mechanics, and try and put things together. And so I don't have I mean, there are many popular books on this subject and many popular lectures which you will find. But if you really wanted to understand things at a deeper level, you'll have to study, the subjects of GR and quantum mechanics and quantum field theory more. And that's, I think, yeah.
So, am I audible?
Yeah, I can hear you. Yeah.
So, what is singularity actually? Is a point or is a space?
Well, so we don't understand what the singularity is. The way I drew it on the diagram here, it was, yeah. So we don't have a good understanding of what the singularity is or how it should be understood or how it should be resolved. So yeah.
So if we consider loop quantum gravity, the mass cannot be contracted with after a certain limit.
Yeah, it could be, and there are some proposals in the literature for and we do believe in general that some quantum gravity effects should become important before the singularity is reached. And so maybe there won't be a singularity, and maybe there'll be a bounce, or maybe there'll be something else, or there'll be some other way of resolving the singularity. But I think it's fair to say we don't have a good understanding of how that resolution happens, because that's a resolution which involves strong quantum gravity effects, as opposed to all the effects I was talking about today, including Hawking radiation, which involves just putting together what we understand well about quantum mechanics with what we understand well about general relativity. And so, even though these, as I said, Hawking radiation has not been observed because the temperatures of astrophysical black holes are so small, it's theoretically on a very strong footing because there are the ingredients that go into it we understand very well. If you wanted to understand what happens at the singularity, you would need to understand some new physics. And that new physics we don't understand because we don't have access to empirical data that will help us understand that new physics. And it has not so far been possible to just use theoretical constraints to understand the physics that's important to understand the singularity.
So, if we somehow reverse the time, so can we model how the singularity is formed?
I'm not sure I understood the question.
If we have a boiled water and we reverse it, we can find our water normal stage. So if we start reversing the time, and can we find that what happens before singularity?
In this thing I discussed the singularity. In the story I discussed, the singularity was not particularly important at all. The singularity was something that occurs in the story I described, was something that occurs at the end stages of black hole evaporation, and was not important for most of the Hawking radiation that was being emitted, which was being emitted from the horizon, which is just far away from where the singularity is. And so, in what I discussed, the singularity was not important. And the question of reversing time was a question of using this Hawking radiation that's been emitted to reconstruct as much of the information possible about the initial state of the black hole. Now, the fact that there's a singularity might prevent you from reconstructing everything about the initial state, but most of the information is in the Hawking radiation because information comes out with energy. And so most of the energy is just dissipated into Hawking radiation when the black hole is still big. And, so most of the information is there, and that's the kind of question I was asking. The kind of question you're asking about the singularity is something that, as I said, we don't really have a good theoretical and certainly no experimental handle on. And so there's no really good way to, when I said reversal of time, I was just trying to ask, from the Hawking radiation that's emitted, can you reconstruct the initial state? And the answer is yes, even without knowing exactly what happens at the singularity.
Sir, you were talking about some solutions in which one solution was a black hole. Are there some other interesting solutions? Like some people talk about white holes. Is it also a solution?
Yeah, I mean, in fact, it's the same solution. So, if you draw this Schwarzschild solution that I wrote down, this exact solution, if you were to draw its full space-time diagram, it would in fact have both a white hole and a black hole. It's what's called an eternal black hole. The solution that I wrote down. That Oppenheimer-Schneider solution that I mentioned has only a black hole. It doesn't have a white hole. But the first metric I wrote down has both a white hole and a black hole. Of course, there are very many interesting solutions in general relativity, right? There are, because it's a rich mathematical framework which allows you to find many interesting solutions.
All right. Thank you very much once again. So I guess
Okay.
we can now come to a formal close of the session. So I'm sure all of you, many of you have quite a few other questions which are still lingering on your head. So do feel free to write out to us, or mail it to us, or put it as a comment on the YouTube section. We'll definitely get it answered. So first and foremost, thank you very much, Professor Suvrat, for giving this wonderful lecture on taking us from some of the most concepts which we thought we would never be able to understand to like giving it in a very intuitive fashion. So thank you very much for that. So I hope to see all of you once again on tomorrow at 3 p.m. when we have Professor Kavita Sutar of Chennai Mathematical Institute, who will be giving an introduction to what group theory is under the disguise of kaleidoscopes and reflections. So I hope to see you all there. Once again, thank you very much, Professor Suvrat, and all of you for attending this session.